Alright, in this video we're going to look at how we can quantify the acidity of different compounds. And so we're going to look at numerical values, and specifically pKa values, to determine which compounds are more acidic or basic. So, if you remember from general chemistry, this is sort of a general acid-base reaction where we have our acid, it's donating a proton to water to form the conjugate base and the hydronium ion. And the equilibrium expression for this reaction has H3O plus and A minus, the product concentrations in the numerator, and the concentration of the acid in the denominator. And so the stronger the acid is, the more it will dissociate, and the bigger the Ka value will be. Now, one disadvantage of Ka values is that sometimes they're kind of hard to use, right? So they tend to be in the range of 10 to the minus 50 to 10 to the positive 10. So they have really large exponents, and they can be kind of hard to work with. So very often what we do is, rather than using Ka values, we use pKa values, where we take the negative log of the Ka to give us the pKa. And these tend to be numbers from negative 10 to 50, and so they're much easier to work with. But the important thing to remember is, right, bigger Kas mean stronger acids, but lower pKas mean stronger acids, because we're doing the negative log, right? So one analogy that you can use to help remember this, right, lower pH we know means more acidic, so lower pKa means a stronger acid. So we have several tables in different places in your textbook. In this chapter, there's a big table, and also in the appendices, and I think in the front cover, we have other tables with lots of pKa's for different acids. And because these pKa's are the logs of Ka's, each unit of pKa represents a power of 10. So because sulfuric acid has a pKa of minus 9, right, it's 100 times stronger than hydrochloric acid, which has a pKa of minus 7. Right, 2 units of pKa is 10 to the 2, or 100 times different. We can also use these pKa values to determine the basicity. So in all these tables, they give us the pKa value for the acid, but this also tells us about how basic the base is. And in general, the more acidic a acid is, the weaker a base its conjugate base will be. So sulfuric acid is a very strong acid, meaning its conjugate base is a very weak base. And sometimes it can be helpful to do this numerically. So from Gen Chem, right, we know that if we have a conjugate acid-base pair, the pKa of the acid plus the pKb of the conjugate base is equal to 14. So we can get a numerical value for the pKb value. So to get the pKb, we'll just do 14 minus the pKa. So for example, if I compare Cl minus, whose conjugate acid is HCl, right, 14 minus a negative 7 is going to be 21, whereas this compound, right, its conjugate acid has a pKa of 44, so 14 minus 44 is negative 30, right? The lower the pKb, the stronger the base is, so this is a much, much, much stronger base than the chloride ion. So another thing that we can do is, when we have a acid-base reaction, we can actually determine whether, when this reaction is at equilibrium, the reactants or the products will be favored. And so in general, the way the book describes it is, right, the higher pKa is the weaker acid, and it says that equilibrium favors the weaker acid. The way I like to think about it is a competition between the two acids, right? So I've got the acid on the reactant side, I've got the conjugate acid on the product side, right? And whichever one is stronger wins. And because acids are proton donors, right, water has a lower pKa than this compound, and so this is a stronger acid, and so it's a better proton donor, and so it's going to force the reaction to the other side. So the stronger acid forces the reaction to the other side. So in this case, the products are going to be favored. Here's another example. In this case, water has a pKa of 15.7. This guy has a much smaller, a much larger pKa, right? Again, the smaller the pKa, the stronger the acid. So water is a much stronger acid than this guy, and so this is going to really force the equilibrium to the other side, and so this isn't even really an equilibrium, right? There's such a difference between the pKa values that this reaction really goes to completion. So if we look at a couple examples, if we were to use pKa values to determine which compound is more acidic, so I've got ammonia and ethanol, and so I would go to the table and look up the pKa values for each one. So I have ammonia, its pKa is 38. I have ethanol, its pKa is 16. Right? A lower pKa value means it's going to be more acidic. If I want to determine which compound is more basic, I can still use the pKa values, but I want to look at the pKa's of each of these compounds' conjugate acids. So here is the base, right? Its acid has a pKa of 25. Here's the other base. Its conjugate acid has a pKa of 16. But the pKb is 14 minus the pKa. So this guy has a pKb of minus 11. This has a pKb of minus 12, right? And so just like the pKa's and the acids, the lower the pKa, the stronger an acid is. Well, the lower the pKb, the stronger the base is. So this guy is going to be the stronger base. Or you don't have to go through this, right? We can use the relationship that, right, the stronger an acid, the conjugate acid is, the weaker the base is going to be, right? So when I look at these two, right, this conjugate acid is going to be stronger, so its base is going to be weaker, right? This thing's conjugate acid is is weaker, so the base is going to be stronger. So this guy is the more basic. All right, if I look at whether reactants or products will be favored at equilibrium, I need to compare the pKa's of the acid. So I need to find the acid on the reactant side, and I need to find the conjugate acid on the product side. And so we can see this thing goes from being neutral to being negative, so it must have lost a proton. So this is my acid, and then the OH minus accepts the proton to become water, so this is the conjugate acid. And so I'm going to compare the Ka's of these two compounds. So the reactant, the conjugate acid, has a Ka of 9. The conjugate acid, the water, has a Ka of 15.7. Right? And so the lower the pKa, the stronger the acid. Right? So essentially the way I think about it is, in the competition between which one is a stronger acid, this one wins, so it's going to drive the equilibrium to the right, and it's going to be product favored. And because there's a 6 orders of magnitude difference between the Ka values, it's going to be strongly favored. The products are.